Okay, so today we'll talk about streamlines, path lines, and streak lines. And here we are considering an Eulerian framework, and we assume that we know the velocity field. So the velocity field is given by u as a function of space and time, and for a steady velocity it's not a function of time, so then it would just be a function of space, but if the flow varies with time, then you have the dependence on both variables. And we assume that this velocity field is known. So the first set of lines to define this field is the streamlines. And the streamlines are curves that are always tangent to the fluid velocity throughout the flow field. And so in the case of an unsteady flow, the streamline picture changes continuously as the flow evolves. So every realization of a streamline picture is a snapshot of the velocity field at a given time. So it's an instantaneous picture. So consider a 2D flow. Here we have axes x and y. And let's say a particular streamline looks like this. That means that the velocity at a given point is always tangent to this streamline. So this might be u at this position x, given time t. And it has components, horizontal velocity u and vertical velocity v. Now, the streamline segment at this point xy is given by ds, and it consists of components dx and dy. And so from simple trigonometry, you realize that the equation for the streamline is simply given as dx over dy is equal to u over v. Or in other words, dx over u is equal to dy over v. And so if you want to find the entire streamline here that I've drawn, not just that infinitesimal segment, then we integrate dx over u, dy over v. And so this is the equation for the streamline throughout the flow field. Now, path lines describe the trajectory of a given particle. So I've introduced this notation before. Here the position of the particle is given as rp, which is the location that is defined at the time t, and the initial conditions for each particle are 0 and t0. If you know the initial location of a particle and you know the flow field, then you can calculate rp as we go through time. So I should clarify here, r0 and t0 are the initial conditions, not independent variables. So if I draw a coordinate system in 3D space, x, y, z, and I have a particle that is at my initial time t0 at location r0, and I know the flow field, then I can follow the trajectory of this particle over time. And later on, my location will be given by r, which is now a function of time and determined by the initial conditions r0 at time t0. And so in this case, the relationship between the position and the velocity field is simply given as dr dt is u of x and t at the location x equals r. So it is just u of r and t. Now, in order to find the position r, we just integrate this equation. So r of t and r0 t0 is simply the integral from t0 to t of u of r and t dt. And the variable of integration we denote with a dash. And I've mentioned this before, just to clarify, here r at t0 is the same as r0. That's just a shorthand. So this is the equation for the path line down here. Okay, finally, we have the streak lines. Streak lines are lines that connect fluid particles that pass through a given point. So let's consider the origin to illustrate this. So we have let's say we have a 2D field here, and we have a unsteady flow. So let's say the first particle that comes through, passes through the origin, came from here, and then gets deflected up in this S shape. So this is the path line where the location is that of the position of particle 1. So we say R1, this particle passes through 0 at time t1. Then at time t2, we have a different particle that came from, say, further up here and is following this trajectory. So this is x equals r2. And so the point is here, our flow field varies over time, right? If our flow field would be steady, then all the particles would always come through the same path line as before. So R2 goes through 0 at time t2. R3 might be this particle here. R3 through 0. So at time t5, what would the streak line look like? Well, R5 at t5 is at the origin. R4 has moved along a little bit, so it's somewhere here. R3 is further along even. R2 is up here, and R1 would be up there. So the streak line at t5 would look as follows. This is the streak line at t equals t5, where, for example, the green dot here is the location R2 at time t5. So, in summary, you can imagine that streak lines are observed when dye is released continuously at one given point. So the point that has passed through the early origin at the earliest, which is R1, our particle R1, is the furthest from the origin when we calculate the streak line.